the best real-world application of near-term and future quantum computers, quantum network, and quantum sensors. And at the same time, I'm also very interested in illustrating the boundary between quantum and classical. And especially if we want to claim something about quantum advantage, we sometimes need to be careful to make sure that it is not outperformed by some classical algorithms. So those are could summarize my research interest. And today, the title of my talk was simulating quantum algorithms using industrial level medium scale LLM, or a short name of this talk was also Grover GPT, which is a primary stuff that we have created and fine-tuned and from some existing large language models such that it can actually learn and trying to mimic some output of quantum algorithms. Okay, so let me firstly start with the introduction, and later we will get to a little bit technical part. And if you have any questions, you can ask in the middle. Um, okay, so let's start. So we know that quantum computing is to believed to have the potential to have the computationally advantages against classical counterparts were one of the first example of advantages of quantum computing that people show is Shor's algorithm, where people show that this is an algorithm that could run in polynomial time that potentially breaks some common asymmetric cryptography. And then that shows significant potential for this technology that motivate us here who are trying to build quantum computers. And okay, however, so if we can illustrate it more precisely, we can try to draw a Venn diagram, and which is like a complexity class of lots of similar to P and NP. We could have lots of complexity class definitions. And then in complexity theory, the analog of P is called BQP, and the analog of NP is called QMA. So here it is a version of the Venn diagram that some people believes, or many people believes, and as a summary, actually many people believes in BQP is larger than P, which means that some quantum computing algorithms might be much faster than all possible classical algorithms that could solve the same problem. So this is a term we nowadays call it quantum advantage. And more precisely, we are interested in trying to figure out where are applications of the star here that is inside BQP but not inside P. However, the current quantum hardware is very noisy. So noise is a significant problem about our current quantum computer. So now I think we are maybe around the end or already end the so-called NISQ era, which stands for near-term intermediate scale quantum era, where we are able to have 100 to 1000 qubits, but we can only apply 100 or maybe to 1000 noisy gates. And the current device, generically, they cannot do error correction fully. So there are some early fault-tolerant experiment about fault-tolerant quantum computing that has been realized in recently from 2023 to this year. And there are lots of experiments going on, including Google's experiments about quantum memory and also quantum error detection code and a few logical gates that can be applied to the quantum memory, and also some experiments about magic state distillation and also some related methods. So it seems that now we are able to try to have a little bit of fault-tolerant technology that can be realized. But however, due to the complexity of especially the mid-circuit measurement, fault-tolerant logical quantum computing might be realized in the next 5 to 10 years, although it might require very, very hard work. So this picture itself is produced in 2023. I believe that it must have a lot of updates nowadays. And then people are previously interested in this NISQ regime where they can have relatively modest gate error and they can have a large number of qubits, and we hope that it can solve some important problems in this region. At the same time, nowadays many people also try to develop some new technologies that trying to bridge RE fault tolerance. But however, it is still very challenging at this moment that how to improve the gate fidelity and also trying to improve the quality of a stable quantum memory. These are like a challenging tasks that people want to figure out, especially about hardware. So, okay. So then, based on this current status, what is the practical boundary of those quantum advantage with or without quantum error correction? So, to study those phenomena of quantum classical separation, so sometimes we try to draw this brief diagram, and in the x-axis is the number of qubits, and y-axis is the noise, and then there might be a line separating quantum and the classical. We believe that maybe in the large regime of number of qubits, but a small noise, perhaps we will have a quantum advantage. But because the current devices are noisy and implementing error correction is kind of challenging, so then maybe there are certain regime where noise is high and the number of qubits is relatively lower, then maybe classical devices might be enough. So if we believe in this picture, this like illustrating a practical boundary of quantum advantage is very important. And the boundary can be maybe time complexity or space cost or hardware cost or energy cost or some other consumptions. And then that picture in practice, instead of using complexity theory, can also be helpful for decision makers trying to use a suitable technology with a limited amount of budget. So in this talk, I will primarily try to illustrate another method. I hear already many talks about tensor networks, which is fascinating. In this talk, I'm going to talk about a little different method, and which is trying to use large language models. So we start from training some large language models that can perform some basic function of simulating quantum circuits. At this moment, I think we are confidently saying that it seems our LLM is able to understand this basic Grover's algorithm in some sense, and also it can generate some correct output. However, I'm not sure if that can be generalized to more general cases, and this is something still under development. But I think this at least just show that LLM has a capability to understand some of quantum algorithms, and we hope that maybe with a help partnership with, especially with industry who have lots of resources on training those advanced large language models, maybe we are able to try to also integrate the force of simulators and also tensor network calculations. We maybe are able to simulate larger experiments of quantum circuits than we think. So this is a primary topic of the talk. Although it is currently only a baby that it can only realize some basic function, but maybe in the future we're able to do much better. Okay, so before that, I will give some basic introduction of our way of simulating this and trying to make an LLM to simulate a quantum algorithm and what do we mean by that. And later, I will briefly show you some results and discuss the corresponding technology that's underlying this development. Okay, so at the beginning, I will just briefly introduce what is our definition that we use as a quantum computer or quantum Turing machine. So abstractly from mathematics and especially linear algebra, the input and output of quantum computing is very simple. So the input is actually a sequence of classical description of quantum gates, like C0 or a T-gate or hard-mark gate and so on. So this is usually called a quantum algorithm or a quantum circuit. And the output are based on quantum mechanics. They are samples that is generated from probability distributions on every bit string. And for instance, here it is a very simple example of a probability distribution on the bit string. So the quantum machine actually generates samples from it. So technically, it can be called as a sampling machine. So okay, so this is this quantum computer's input and output, and for universal quantum computing. There are a few comments about this definition. So firstly, we basically cannot apply too many gates, otherwise it's too complicated. And usually we call the circuit depth polynomial in number of qubits. That is considered as efficient, roughly speaking, where the circuit depth is exponentially in number of qubits. That is considered hard. So, and in this universal definition, and we can like make it more specified by setting different initial states. For instance, here I default imagine that it could be set as a zero state. But however, it is not loose of the generality because you can merge your state preparation unitary into part of your classical description of the quantum circuit. So without loss of generality, and one can assume the input state is a zero state. And also you can change the B-string distribution to some other distributions. So that is basically changing the computational basis to some other basis. And they can also be understood as part of the quantum algorithm. So without loss of generality, we can assume the quantum Turing machine is just such a simple object. Okay, so we know that real quantum devices can realize such a task. However, if the output can be calculated efficiently using a classical computer, so either you can calculate the distribution directly or you can generate samples, that is called classically simulatable. That is, in some sense, a sufficient condition to disadvantage quantum computing. Because if someone can simulate classically, and just like many tensor network experiments that people discussed recently, and also some other optimization experiments, then that means that there is no significant quantum advantage. And for instance, we know that Clifford circuits can be simulated classically. So that is a famous statement in quantum error correction. So the power of quantum computing should really comes from a combination of Clifford circuit plus the T-gate. So that can generate universal quantum computing. Otherwise, it can be simulated classically. So then, instead of addressing the question about the boundary of quantum advantage, so we can think about just address the boundary of classical simulatability, which seems to be an easier task. So our work, as I mentioned before, Grover GPT is basically trying to use this model and put those quantum circuit in, trying to train an LLM and let it generate probabilities distribution or some samples from it. And the reason that we believe that maybe LLM is useful because LLM is one of the most powerful machine learning models with the largest scale at the moment. And people has lots of experiences on training that has been accumulated recently. And it shows evidence that LLM, firstly, it can be connected to external compiler. If LLM cannot do it by itself, it can call a Python compiler and trying to process it there and generate the feedback. If it cannot learn logical computing, and it can also maybe connect it to a future quantum computer directly, serving as an agent. But at the same time, LLM maybe it can discover some interesting classical algorithm, because we know that LLM now shows evidence that it can actually discover some new theorems in math. So we believe that quantum algorithms is also kind of a mathematical problem. So maybe we're able to say that those LLM can be more powerful than we expect about finishing some tasks about classical simulation. So that is the motivation of us trying to do this. And the model description is that we basically re-pre-train and also fine-tune from Llama's 3.1 8 billion model architecture. And originally, this model is trained over a huge amount of training data. And basically, we re-pre-train using some um, limited number of quantum search instances and also fine tuning it using some AI technology. And then we also we basically collect the input and output of Grover's algorithm and trying to train it, and then trying to ask it to generate the output. And we show some. We find that the machine seems to be very interesting and has some interesting behavior. Um, Firstly, Grover's algorithm, I believe that many of you are already very familiar with it. It's a database searching algorithm and using quantum computers. For a database with n data, the algorithm could search a target within the square root of n time, which is outperforming all known classical algorithms. However, we need to remember that this definition is a little subtle about its quantum advantage because its advantage is basically coming from the number of query for the oracles, and the oracle can actually search faster. So basically in this sense, if we just directly submit this kind of circuit to a real quantum computer, ask it to just directly run, it not by itself shows quantum advantage. But it is still an interesting experiment that instead of observing quantum advantage, we just want to say if the LLM can, in some sense, understand circuit. So, okay. So as a summary, is that we can try to set the input basically as a QASM circuit, which is one of the standard quantum circuit programming language. And we can show that the prompt example, like trying to pair the input and output. And here is an example of the prompt, a basic prompt. If we want to act, I want you to act on as a quantum computer, and then we specify the Grover's algorithm. We give the circuit and ask it to generate the output. Note that the Grover circuit has a marked state. So in this language, we actually just directly say it in the marked state, and then actually the circuit just directly say it as a shortcut for just directly see its marked state. But however, the marked state language can also be removed and does not significantly lower the performance down. So in some sense, it seems that the ARM actually implicitly trying to reverse engineer such a circuit and identify what is the correct search target it can generate. So in that sense, it may not happen is that we are not sure if the circuit actually nor the matrix algebra, but instead, if you give them a large number of instances, the ARM could actually know where is a hidden search target that is inside the circuit. And overall conclusion of our first paper in this area is that firstly, we show that the model can outperform some general purpose models like GPT-4o because the general purpose model didn't see enough like a quantum circuit. And so if we retrain it, and with a reasonably large number of samples, and then the model could practice and learn and make it better. And also the model can generalize up to 20 qubits by only look at a few qubit examples. And also we make sure that the model can actually learn features of quantum search instead of just learn a classical searching algorithm. Because if the model reverse engineer the marked state, and then maybe we say that, oh, it is just a classical search algorithm. But however, so because they are still a minor piece of the unmarked state probability amplitude, so we can actually try to test that amplitude in order to see if we can actually, if the model can actually learn the features of quantum searching instead of only the classical searching. And also, we find that at the earlier stage of our project, we already realized that if we can improve the QASM language in some degree, some prompt engineering framework can be developed to make the algorithm that performs better. And this is a simple training curve that we try to take Llama 3.1 open source model and trying to train it. So we in our lab we don't have that many training resources, so we can only play with some minimal scale baby model. But however, in the future, and I believe that maybe this can serve as a prototype for larger scale experiment. And then we include Llama 3.2 and 3B and also DeepSeek V2 Lite as benchmarks. And we find that actually after sufficient amount of training and especially some like a prompt engineering, and it actually can have a significant enhanced accuracy. And overall, the fidelity is also good for the output. We define the accuracy to be finding the correct target, but the fidelity or infidelity is basically about the correctness of output probability amplitude. It is a more quantum stuff, and then it includes the unmarked state probability. So then that seems to be a more comprehensive identification. And what we find is that actually for predicting the output, and actually our model also seems to capture that feature that the Grover search is a quantum algorithm, that it has some like unmarked probability amplitude there, and then so that it shows that our model actually can capture it. And another example that we test is about generalization, which is that we only ask LM to learn only up to, for the data sets to be only up to like 10 qubits, and we try to generalize it to higher number of qubits, and it seems that it still has some significant accuracy. Although the fidelity is also okay, but infidelity is also okay, but and also the accuracy is also okay, especially if we generalize it higher. But we generically believe that if we have more number of qubits, and then the accuracy would would decay significantly. And also, we also show that this LLM itself is robust and against like various data sets. And if we change different data sets, we change the learning rate, we change some hyperparameters overall, and actually the accuracy is still kind of okay. And also, we find that those two metrics about accuracy and fidelity can be aligned with each other. And this is a figure that shows our various experiments, shows the coherence that these two metric. If you get one, you can also get another one. Okay, so and further also furthermore, so we test it further by change some training details, and that is called ablation experiment, and to make sure that it is stable if we change the parameter, and that stability means that this observed phenomena seems to be not a unique instance, but instead something that could happen generically. And also we find, of course, if we trying to reduce the size, making it more compact for the QSM language, and then that will also improve the capability of the model. So if, for instance, in the original QSM language, so the oracle is written as, firstly, it was a Hadamard applying to array qubits, and from 0 to 3 qubits, and then we can shorten it by, instead of listing all the individual qubits, we can try to say there is a qubit Hadamard that applies directly to all qubits. If we make it more compactified like this, and then it will be, the performance is also going to be better. Moreover, so the second later we actually update the model to integrate more functions, and we can observe that internally and what happens in the model. So we use like two different new technique. Firstly, it was quantum native tokenization, and secondly, it was about chain of thought, which is some recent reinforcement learning based techniques that trying to educate the machine to think as humans. So we slightly update the metric, so you will observe that the number is slightly different because in the second version, we use fidelity, real fidelity in quantum information science as a metric. But before we define the fidelity as the distance between the amplitudes, but now we define fidelity to be the norm in define for fidelity of the quantum state. It's more like a direct definition from quantum information science. And those techniques in the second version, Grover GPT-2, can be very easily explained. So the first part is about so-called quantum improvement from the basic tokenizer towards quantum native tokenizer. So the idea for the tokenizer is the following. So for the large language model, if you have a model, and then the model will take your data as take your language as tokens, and it will try to split your vocabulary to several pieces, and they understand those pieces as a whole instead of understand them independently for each characters. So this is a feature of the human language. Like sometimes we directly use like letters. We directly use like words and in terms of individual letters. And usually it's words that has a coherent meaning, or paragraphs, or like a phrase that has a coherent meaning. So it is similar for quantum circuit programming language that is also in some sort of similar to natural language. And because we know that describing quantum gates, we cannot split them. Because X gate cannot be split like for the words like X and gate and so on. Then the machine cannot understand it very well. Although it can still perform okay, but we feel that this tokenization is kind of necessary to do. So we try to change the vectorization strategy when we map words and tokens to vectors, such that the output, the input of the model will tokenize it correctly. For instance, we put the description of X and H gate together, and we find that definitely that will reduce our vocabulary because in this case, as long as we remember what is the gates, and for individual gates, we don't have to remember the letters. So that will definitely reduce the total size, total like a combination of vocabulary, which is a more efficient language. And secondly, we can tell the machine a shortcut. So the shortcut is that because we can in order to make sure the machine actually understands what it does, and we just can use COT and chain of thought in order to try to illustrate the machine in each step what to do. And for instance, firstly, the machine could identify where is the oracle in the quantum algorithm. And secondly, it can read those block sequences, and from those block sequences, it can identify the corresponding mark state and also the final state. And and in this simple example, we show the chain of thought for like two different mark state. And then so if you have those like a different mark state, and then it's much easier for you to come out with a probability amplitude or generating samples. So this is not really what's internally the logic that is happening in quantum circuit, but at least it shows you some features. Those like actually LLM can using this way. LLM can understand. Actually, it has some like it can it can understand part of the search target are inside those oracles. So using this way, the machine can reverse engineer what is targeting results. So usually when we tell the machine in that way, so that operation itself will significantly boost the performance after we introduce the chain of thought. And similarly, for the same thing, we actually observe a similar chain of thought like a for existing general purpose model like ChatGPT's GPT-4o, and then we also obtain a similar chain of thought. But however, so the answer of that is usually wrong. So which means that the general purpose, if you didn't train it in that way, they don't understand what happens in the quantum circuit and what is individually happening in those quantum circuit. And yeah. Yeah, sure. Okay, so basically those are the landscape of what we did, and we also integrate with those two technology, chain of thought and also tokenization. And those are the brief summary of our performance, which is better than we also primarily compare the DeepSeek and also Doubao, which is another like a large language model, and we find that actually it also have a good performance. And we also test the chain of thought less, that this method actually educates the machine better, so it has better COT length. And also finally, so we also tested scaling law, which is about how this method could be generalized to larger number of qubits. And also like we compare it with some other simulator, computing it by brute force. And because we tell the LLM the shortcut, so in this basic example, it can actually be faster than at least the state vector or unitary kind of simulator. Okay, so let me summarize the talk because of the limited time. So Grover's algorithm is a simple algorithm and only serves as a proof of principle and a shortcut because our computational power for doing this is really limited. But from this example, we learn that an LLM can make the basic logical reasoning and trying to mimic quantum circuit. And that phenomena, that LLM actually exists. So in the future, what I wish to do along this line is to create an LLM that can be called as a foundation model for quantum that can integrate external compilers and perform simulations, or integrate with external even quantum devices, and can deal with many different quantum algorithms. And also it can guess answers for noisy or noiseless devices by trying to learn lots of data generated from real quantum devices. And I hope that if that was realized, what will be the insight that it could provide about the boundary between quantum and classical. Thank you very much. This is my talk. There are any questions? Yeah.
Very interesting talk. So I want to look at the growers, the oracle you use for the growers. So is it just with one correct?
You mean the mark state? We include a single mark state and also multiple mark state. And for instance, here it is an instance of this COT is an instance of two mark states where we actually in this situation that it was two mark states 0111 and 1101. And the task technically for such a baby LLM is trying to find such a target from the oracle.
So is it true that the classical algorithm can just read from the description, just read the correct answer, and the non-trivial thing is to produce the probability?
I think even for that, it's gonna be very hard for LLM. So LLM itself, in this level of number of parameters, and then it's very limited capability in logical computing. So even for instance, a standard example is to compare 3.11 and 3.9. The machine does not know which one is larger. So then when I tried to directly ask it to do logical computing like matrix algebra, but it does not work. But however, for Grover, it's simple enough because the information was contained in the oracle. So I decided to try to teach this shortcut. And then such that if you didn't read the internally what happened in COT, and you will feel like this seems to be a generic simulator because the input is a like a quantum circuit and the output could be probability and the samples. But however, in the future, I hope that I could do some larger experiment. But currently, the size was really limited. It is not as smart as like some more like a much larger training parameters and models with a larger size.
GPT to simulate finite state growers on.
Yeah, with benchmark it does not work. If you put the same command to GPT, GPT does not give you correct answer. But you usually for that I need to clarify. You need to ask GPT, do not use external compiler. Otherwise, the Grover GPT will just directly call a Python package and try to simulate there and just directly give you the answer. I want to integrate that function to my LLM as well. Yeah, but if you stop GPT from doing that, ask GPT to like read by itself, GPT cannot do it because GPT does not see that many Grover circuit comparing to the model that has been fine-tuned.
Okay, so thank you very much again, Junyu.
Thank you.